Hey everybody, Mr. Bress back here with our third lecture on the in the evolution unit. And here we're going to kind of extend our understanding of how we know how old the Earth is. So let's get started here. I'm going to come back to the presentation and pick up where we left off last time. So what we figured out to begin with was we can measure the age of the Earth or date back quite a few years, over 10,000 years, simply by counting the rings on trees and kind of matching up or bridging older trees that had died by sort of this signature, this barcode of the different widths of rings. Then we introduced this new concept of the decay, the radioactive decay of carbon-14 out of dead organisms. And we showed that carbon-14 decay, that method of using that to determine the age of something, matches up very accurately with the known dates of old artifacts and some of these old trees that we had originally counted the rings on. So we're really confident in this method of carbon-14 dating to get us back 50, maybe even 100,000 years. And then the question, though, is, are there techniques, are there ways of knowing if the Earth is actually older than 100,000 years? And in fact, there are. And the way that we do that is, so the question then is, can we date rocks? Well, yes, we can, not in the way that the picture is showing here, but rocks are made up of the same atomic elements that make up everything else on Earth. And we can use special features of how rocks are formed and the same sort of radioactive decay we learned about in carbon dating to measure the age of rocks. And through these methods, the scales of the age of the Earth get much, much older. And so we're going to start as an example. There's many examples of this, but we're going to start one from this example of igneous rock. And there are three types of rock: igneous rock, sedimentary rock, and I can't think of the third one right now. Maybe you can think of that one at home, but we're going to use igneous right now. And we typically think of igneous rock as this molten lava of volcanoes. And you've all seen sort of pictures of molten lava streaming out of the top of a volcano. But the same magma that pushes up out of a volcano can push up into other layers and form layers of rock in the Earth. And this is called intrusive igneous rock formation. Another place where we kind of have seen magma pushing up is on the sea floor, where the sea floor sort of spreads out as this igneous rock, this magma pushes up. And that's sort of the driving force of moving the continents, of this continental drift. And the continents aren't all in the same place that they've been in that they are right now. They haven't always been that way, right? Maybe you've heard of like Pangea or other sort of where the continents fit together and they've sort of moved over time. And this pushing up of this magma is the driving force of that. So this is sort of where earth science and biology sort of converge. An interesting feature of igneous rock or molten lava is that when it comes out, it carries many elements, but one of the elements that makes up igneous rock, or two of them, are potassium and argon. And what's interesting about this is when the molten lava comes up, it's hot. I don't know the temperature of it. Maybe you could look that up, but you can imagine it melts everything. It's very, very hot. And argon, by its nature, is a gas. So when argon gets exposed to the atmosphere, when it originally is formed, um, it bubbles out and it leaves as a gas. And in fact, it does that even in those intrusive formations here, that it's so hot that the argon gas can percolate up through the layers above it and leave the newly formed rock. So what this means is when a molten rock comes up and forms its initial layer, either pouring out of a volcano or moving into a new crack, when it comes up and starts to cool and harden, all of the argon is gone. So there's no argon left in this rock, and that starts this sort of geologic clock with no argon. And but there is potassium in there. And here's where this gets interesting. So potassium, like carbon, comes in multiple flavors. And there are two that we're interested here. And these flavors we call isotopes. Iso sort of meaning the same. They're the same, but they're slightly different. It comes in potassium 39 and potassium 40. And both versions of potassium have 19 protons. That's what makes potassium potassium. It has 19 protons. And I'll quickly show you that, so you don't think I'm a liar here. I'll show you that on the periodic table of the elements here. Here's potassium. It's number 19. It has 19 protons. That's what defines an element as being potassium. However, as we learned with carbon, there can be different isotopes or different flavors that have different neutrons. So here, potassium 39 has 20 neutrons and potassium 40 has 21 neutrons. And this potassium 40 is radioactive. And the interesting thing about the radioactive decay of potassium 40 is that it decays to argon. And this happens in a much slower rate than carbon 14 decays to nitrogen. And so in a lab, you can measure how much energy is released from potassium 40 or from carbon 14. And scientists and physicists can then calculate how much of that element is lost in a given time frame from how much radioactive energy is emitted. And this is way beyond, but energy and mass from Einstein's equation, E equals mc squared, are the same thing in physics. That's like over my head a lot, but scientists can use that knowledge to show that this rate, that half of the potassium 40 will turn into argon 40 in about 1 billion years. This is a much longer time scale than the carbon 14, but it relies on identical principles as what we learned about with carbon 14. We'll move on to our lecture guide here in a second, but what happens then is, as each layer of rock, as scientists measure it, if there's argon there, we know it had to come from potassium 40. And as there's more and more argon there, we know that rock must be older and older. It's like the inverse of what we saw with carbon 14. With carbon 14, the carbon 14 disappeared and we knew the rock was older and older. And here it's easier to look at argon appearing. If you wanted to, you could think about this as potassium 40 disappearing, right? So here you see a lot of white circles that represent potassium. And as we get older and older, we see fewer of those. But maybe it's just a little bit easier to think about it in the positive aspect, that the appearance of argon is measured, we know very carefully at the time frame when we'll see argon. So the half-life of potassium 40 is 1.25 billion years. So when we see the same amount of argon 40 as potassium 40, we know that that rock is 1.25 billion years old. So let's move over to our lecture guide here and let's fill in what we know so far. All right, so I'm gonna click here and open up our evolution lecture guide. All right. So I have this in Notability. Okay. So radioactive potassium has 19 protons. That's what makes it potassium. If it had 18 protons or 20 protons, it would be a different element. And unfortunately, I can't remember them off the top of my head right now, but I'm sure Mr. Strauss or another Mr. Nelson, our chemistry teachers, could tell you right off the bat. But potassium has 19 protons. And to be potassium 40, that must mean it has 21 neutrons. So fill in the arrow to show the radioactive decay of potassium. So potassium 40 decays to argon 40. Okay, so the appearance of argon tells us a little bit about the age of the rock. And so in this image below, which layer of igneous rock is older, A or B? Well, we'll see soon that layers of rock, this idea of superposition, that layers above are always younger and layers below are almost always older. But here we also can see that we could measure the amount of argon here, and lots of argon 40. And here we have a little argon 40. So we know that B is older. So B. So, and there are two ways of doing this. Like I said, you can measure the amount of argon. If it has more argon, that igneous rock is older. But we also know that it's a layer, it's a lower layer. So that's another way to be able to tell the age of that rock. Okay, so let's complete this sentence here. So as igneous rock gets older, it accumulates more argon 40 and loses more of its potassium 40. And just be careful that the chemical symbol or the elemental symbol for potassium is K. So K represents potassium. Because I think P maybe they already used for phosphorus, whatever. So in an igneous rock, so let's look, so this is the same type of chart that we saw before, and this represents one half-life. So after about 1.3 billion years, so this is 1.3 billion years, half of the potassium, half of the potassium has been converted into argon. So if a scientist measures equal amounts of potassium 40 and argon 40, we know that rock is 1.3 billion years old. And we've measured that in the lab. We can predict that in the lab from the same types of calculations that we used to measure the decay of carbon 14. In that specific calculations are a little beyond high school in general, but I'll just let you know that they are really well established. So in igneous rock, if the ratio of potassium 40 and argon 40 is equal, how old is that rock? Well, here you can see that there's 50-50. So that's half, it's a one half-life. Half of the argon, half of the potassium 40 has disappeared and become argon 40. So I know that rock is approximately 1.3 billion years old. And if there's only 25% of the original potassium 40 remaining, that means it's gone through another half-life. And so we move down here, and we can see by our drawing here that only a quarter of the, there's only a quarter of the original potassium 40 is remaining, and now 75% of that is argon 40. So you can see that 3/4 of the pie is argon. So that's another half-life, right? And if we went down another half-life, we would see that this represents only 12.5%. And then this right here represents 6.25%. So, and the distance between these, you might be able to see, is always 1.3 billion years. And we just cut that, potassium 40 in half each time. So if a scientist samples a rock and they see that only 25% of the original potassium 40 is there, and then the rest is argon 40, we know that this rock now is approximately 2.6 billion years old. Okay. So I'm going to see if there's anything more in our slideshow here to continue this. So we talked about the age of these rocks. As potassium 40 decays and becomes argon, we can determine that the age of the rock is older. And here, this is the same thing we just did in the lecture guide, that the half-life of potassium 40, half of the original amount disappears every 1.3 billion years. So it goes from 100% to 50% to 25% to 12.5% to 6.25%. And at that point, we are at 5.2 billion years old. And that is about the age that scientists have calculated the age of the Earth. There's many ways of sort of confirming this. And I want to get to one super secret, what I've called the super secret challenge question. And I'm going to highlight that in our lecture guide right here. Let's start this. Okay. So scientists had predicted, prior to learning about this decay of potassium and the age of igneous rocks, scientists had predicted for many years that there are cracks in the ocean floor where the sea floor is spreading. And new magma has pushed up and the sea floor spreads. And that's sort of demonstrated here where the magma pushes up and the sea floor spreads out. And so I said you could see this for illustration. And there are others where the seafloor is called subduction. You might have learned about this a little bit in middle school, where parts of the crust of the Earth dive back down into the core and get melted away. So there's parts where the seafloor spreads, and then there's parts where it kind of dives back down to get melted and recycled back up. And this happens over the course of hundreds, if not billions of years. So now I say, look at the image with the striped seafloor and the magma pushing up. Which area of the seafloor is older, A or B? So based on this theory, scientists would have expected that B would be older, right? It had gotten pushed up originally, then pushed out, and new layers get pushed. And this older rock is out here, and the younger rock is there. So scientists would have predicted that B is older based on this original theory. So then which area of the seafloor would you predict has more argon 40? Remember, there's no argon in this rock initially. So here there is 0 argon 40. And then maybe we start getting a little bit here and a little bit more here and a little bit more here and a lot more here. So originally, scientists that had predicted that this happened, and they had reasons to believe that, would have predicted that this layer of rock here, B, would be older. Then this technique that came out that says, hey, you can predict the age of rocks by determining how much argon 40 versus potassium 40 is there. So in this older rock, you would predict that B would have more argon 40. It's older. B equals older equals more argon 40 equals less potassium 40, okay? And guess what? Scientists measured it and they found exactly that there was the exact amount of argon 40 that they would have predicted for this age of rock. And some of that was, well, they kind of like based on where animals were and other processes, they were like, okay, there's the continents must be moving at about this rate to get to where they are now. And that means that this much new rock would have to come up and spread out at this rate. And they found exactly what they predicted. And this is how science works. You don't just accept something new without testing it. And it's just kind of like the carbon-14 being confirmed by ancient artifacts. This seafloor spreading and this accumulation of argon 40 matched exactly the predictions that scientists had. And more recently, scientists have predicted and identified that the magnetic poles of the Earth flip in a very sort of clockwork fashion. And there's other ways that scientists have seen that happening. And that matches with the seafloor spreading as well. So the amount of argon matches what they would have predicted for the rate of continents moving, which matches with the rate that they've seen for the poles, magnetic poles flipping, which is kind of what's actually indicated by these stripes here. So this is a really well-established, confirmed method. So if you were convinced that the Earth is much younger than what the potassium 40, argon 40 ratios indicate, what would you study to try to prove it? What could be wrong with this measurement? So if you were convinced that the Earth is much younger than scientists are predicting, then you should study radioactive decay of potassium 40. And you would have to come up with brand new physics, like understandings in physics and chemistry versus what's happened over the last 30 or 40 years, which this has been tested and retested and tested. You'd have to come up and find new flaws. You'd have to be an expert in understanding physics and chemistry, spend a lifetime studying it, understand the details of how scientists measure radioactive decay of potassium 40, and then discover some error in there that would lead to a massively wrong prediction about this. And scientists try to do this. That's the whole part of science, is we try to disprove each other so that we get to the true truth. And you set up things to show that other scientists are wrong. And when it doesn't work, when you get the same answer that they got, and that happens time and time again, then we as a scientific community really start believing that and can use that as a tool. And that's what's happened with potassium 40 and argon 40. And I'm not here to say that we'll never find something different. It just hasn't happened yet. And if you were a person that wanted to show that the Earth is much younger or maybe much older than what scientists have originally predicted, then here's one place you'd want to start. You'd want to be able to disprove what scientists have shown with radioactive decay of potassium 40. And you'd really want to study deeply physics, chemistry, and biology, and earth science. Okay, so what scientists do is, so this method of identifying the age of rocks doesn't get you the exact age of a fossil, because fossils are laid down in what's called, what we'll learn later, called sedimentary rock, which is they die, they kind of fall to the ground, and then wind carries in grains of sand and dirt, or they fall to the bottom of a river, and new sort of sand and soot and soil kind of like fall over the top of it over years. That's sedimentary rock. But this igneous, especially this intrusive igneous rock, can form layers below and on top of, and newer than when this particular fossil was formed, when this animal died. And so you can identify the approximate or the relative age of fossils by measuring the layers of igneous rock, which was what we have here. And we measure these by looking at the amount of argon 40. That's how we identify the age of all of these rocks here. And so if a scientist aged this rock was found to be 60 million years old based on the amount of argon, and this rock here was aged or estimated to be the age of 200 million years, then this fossil has to be somewhere between, it has to be between 60 and 200 million years old. And if you can find fossils that are in between, luckily, that just happen to die in between layers of igneous rock that are very close in age, you can get much closer to the actual age of this fossil. So B down here is much older, and we know that because it's on a lower layer, and that's just how the Earth's surface and the rock formations go, is that newer rocks are formed on top of sediments are formed on top of older sediments. Newer sediments are formed. But igneous rock can kind of make its way in there. And so this here now, we've dated this between 500 million and 700 million years old. So that means that this fossil in here must be between 500 and 700 million years old. And so that's how we can use the dates of igneous rock to infer or to interpret the age of fossils. All right, so I think that's probably all that we have for this video, but we'll go back over to make sure that we've gotten everything here. So we talked about this curve and being able to see the half-life of potassium 40 at a much longer scale than carbon 14. And one thing that's really interesting is that this potassium and argon clock can be used all the way back. Scientists are so good at measuring the amount of argon that they can date this all the way back from 10,000 to over 1 billion years based on the small amounts of argon that would be here. And then they can use that to say, hey, when I look at this ancient artifact that we know the age of, does my carbon 14 measure match my potassium measure, right? Because it should, it's the same principle. So these metrics should match up. And guess what they do? The potassium argon clock matches the carbon 14 clock. And remember, the carbon 14 clock matches the trees and the known dates of historical artifacts. So things that we can touch and see, like old historical documents and artifacts and rings of trees, can accurately be measured through carbon 14. And that measure matches this potassium measure that extends us way out over 1 billion years. And scientists have found a number of other radioactive decay pairs. Like one of the more famous is this uranium to lead that, measured in the lab by the amount of energy that's produced from the decay of uranium-238, scientists predict that the half-life of uranium-238 will be something closer to 4 billion years. And when we use that measure alongside the potassium argon, those should match together. And guess what they do? So scientists are finding many different sort of different clocks and different ways of measuring the age of rocks or ancient artifacts, and then crossing them across. They should all converge on the same date, and they all do. It's almost like witness testimony, right? So if somebody said, oh yeah, I saw the bank robbers get away in a red car. Well, if one person says it, you're like, okay, maybe that's right. And then maybe you find a witness that was a block down the road and they say, yeah, I saw a red car speeding through this intersection. I thought it was really funny. And then a few blocks later, you'll say, yeah, there was a red light and this red car just came speeding through there. Now you have three different things, right, that all kind of match the same story, that this was a red car that left. And that's what these different pairs of radioactive isotopes do, is they all kind of tell the same story, and scientists use them to make sure that they're right. And so that's what I was showing here, is that this potassium argon dating matches radiocarbon dating, which matches the tree dating. And so now with pretty much certainty, scientists know that the Earth is at least 5 billion years old. And in fact, we can't find evidence that there's rocks that are older than that. So based on a lot of this, scientists are at right now, the Earth is somewhere between like 5 and 7 billion years old based on these metrics. And we're always going to be testing this. And if you wanted to kind of become an expert here, you might be able to discover that, well, it's actually 6.9 billion years, not 7.1 billion. But scientists are pretty sure that it's in that range of 5 to 7 billion years old. And in fact, petroleum geologists that look for oil understand that the Earth is really old, because they're looking for debris of old seafloors that have died, been covered up, exposed to high temperatures and pressures, and converted into oil. So when oil companies hire petrogeologists to go find oil, these geologists really understand they need to know the age of certain rocks so that they can go look for oil in the right places. It's really expensive to just go digging everywhere and drilling everywhere for oil. So oil companies pay a lot of money to these geologists who understand the age of rocks so that they could understand, yes, that's the amount of time it would take for this ancient organisms to be converted into oil, and we should go look for oil here. So, so what do other radioactive isotopes tell us about the history of the Earth? Well, potassium-40 decay is one example of elements in rocks that decay at a very well-known rate and can be used to determine the age of rocks. An interesting thing about radiometric dating is that there are many isotopes that have been measured and can be used to confirm each other. That was this right here, these different isotope pairs, each kind of confirm each other. And radiometric dating is consistent with radiocarbon dating, which is consistent with counting tree rings. And so this is how we know the Earth is really old, and there's a lot of evidence for this. And we can use sort of this age of rocks to determine these age of fossils, like we showed in the previous lecture guide. So that's kind of the three lectures that show how scientists know that the Earth is really, really old, and how we can identify the age of different fossils and different artifacts and different layers of rocks very accurately. So I hope that spurred some thought for you. And from here, now that we know the Earth is really old, we can move on to what could happen in a time frame of an Earth that's 5 billion years old. So we'll see you next time.